Dear students, in today's lecture, we are going to discuss about unit number 1, topic 6, searching for solutions. Before an agent can start searching for a solution, first it must formulate a goal and then use the goal to formulate a problem. As we already discussed that a problem consists of input state, set of actions, goal test function and path cost function. The environment of the problem is represented by a state space. A path through state space from initial state to a goal state is known as solution. Let us discuss how the searching for solutions will be done. A state space is the combination of initial state and successor function. This lecture deals with different searching techniques that uses a search tree algorithm that generated by initial state and successor function. For example, we will create a search tree that finds a route from Arad to Bucharest as per our Romanian example. The root of the search tree is a search node that corresponds to initial state. That means if you look at this diagram, in Arad is nothing but our search node for our Romanian example. The first step is to test whether it is goal state or not, which clearly identifies that it is not a goal state. If the search node is not a goal state, then we should consider some other states for searching solutions. This is done by expanding the current state, that is, applying a successor function to the current state, thereby generates a new set of states. For example, in our Romanian example, we can get three new states: in Sibiu, in Timosira, and in Gerin. Now, we must choose three possibilities to consider. This is known as search. Following up one option now and putting others aside for later. In case the first choice doesn't lead to a solution, then we must consider some other options. After expanding the current state by applying successor function to inArad, which generates three new states. For example, suppose we choose in Sibiu first. We check to see whether it is a goal state or not, and then expand it to get four new states: in Arad, in Fagaras, in Oradia, and in Rimicu Velshia. We can then choose any one of these four or go back and choose Thimosira or Gerin. In our example, after expanding in Arad, we got in Sibiu, in Thimosira, and in Gerit. After expanding in Sibiu, we got in Arad, in Fagaras, in Oradia, and in Remicu Velshia. We continue choosing, testing, and expanding functions until either a solution is found or there are no more states to be expanded. The choice of which state to expand is determined by our search strategy. Let us discuss about general tree search algorithm. The function tree search takes two inputs, problem and search strategy, and which returns a solution or a failure. First, we have to initialize the search tree using initial state of the problem and continue the steps until we get the solution or failure. The conditions are: if there are no candidates for expansion, then return failure. Choose a leaf node for expansion according to strategy. If the node contains a goal state, then return the corresponding solution. Else, expand the node and add the resulting nodes to the search tree until we will get a solution. As we already know that the environment of the problem is represented by a state space. State space is represented by a search tree. For that, we need a data structure. Let us discuss about node data structure. A node is a data structure that contains 5 components: state in the state space to which the node corresponds. Parent node is a node in the search tree that generated this node, and action that was applied to the parent to generate the current node. Path cost is the cost traditionally denoted by g of n of the path from initial state to the current node as indicated by the parent pointers. Finally, depth, that means the number of steps along the path from initial state to the current state. A node is a data structure used to represent the search tree. The state corresponds to a configuration of the world. That is, nodes are on particular paths defined by parent node pointers. Two different nodes can contain the same state if the state is generated via two different search paths. The important points to be remembered is the collection of nodes that has been generated but not yet expanded. This collection of nodes is called as fringe. Each element of the fringe is a leaf node, that is, a node with no successors in the tree. That means nodes are the data structures from which the search tree is constructed. Each node has a parent and a state and various bookkeeping fields such as arrows points from child to the parent. In the previous slide, we defined fringe as the collection of nodes that have been generated but not expanded. To represent fringe, we need set of nodes. The search strategy is a function that selects the next node to be expanded from the fringe. It could be computationally expensive because the strategy function might have to look at every element in the set to choose the best one. Therefore, we will assume that collection of nodes is implemented as a queue. Queue contains several operations. They are: make a queue, which creates a queue with a given elements; empty, which returns true if there are no more elements in the queue; first of queue, which returns the first element of the queue; remove first, which returns the first queue and removes it from the queue; insert element, inserts an element into the queue and returns the resulting queue; insert all, which inserts a set of elements into the queue and returns the resulting queue. The output of a problem solving algorithm is either a failure or a solution. The performance of the algorithm can be measured in four ways. They are completeness, optimality, time complexity, and space complexity. Completeness means, is the algorithm guaranteed to find a solution when there is one? Optimality means, does the strategy find an optimal solution? Time complexity means, how long does it take to find a solution? Space complexity means, how much memory is needed to perform the search. Time and space complexity are always considered as measures of problem difficulty. The complexity is measured in terms of three quantities. They are B. Branching factor, that means maximum number of successors of any node. D. Depth of the goal node, and M. Maximum length of any path in the state space. To assess the effectiveness of search algorithm, we can consider the search cost, which typically depends on the time complexity, and total cost, which combines search cost and path cost of the solution found. References: our prescribed textbook is Artificial Intelligence, a Modern Approach by Stuart Russell and Peter Norvin. The prescribed edition is second edition, but in the market we are having fourth edition by PHS and Pearson.